Right, so we're congregating. There are still people slowly feeding into the room. But I have the great pleasure of introducing our keynote speaker once he gets his Xiaodong Fan from Amazon and the Alexa team. We originally planned for him to start the day as you have seen on the schedule, but you will have to tell us about the vicissitudes of traveling here from that corner of the earth. So, and now we're here. So this rewind your expectations to this morning, and we will start right from there. And this promises to continue the exciting day so far. Thank you.
Thanks, Jersey. My name is Xiaodong. Good afternoon, everyone. Recently, I just joined Alexa, and before that, I spent 12 years at Bing Microsoft. And today, I'm going to present you how Alexa enables the entity-based task completion with a natural language interface. And as Juicy said, that I actually had a very rough trip here due to unexpectedly heavy snow in Seattle. Actually, my original flight was canceled. I rebooked, canceled again. But fortunately, my third attempt succeeded, and I just landed this morning. And also, really thanks to Juicy, Daria, and I think, the Airbnb speakers who are willing to switch the talk with me. So eventually, I could make my talk today. But as you can see, I'm still very exhausted. So please treat me well by not asking me tough questions. All right, so let's get started. So I will talk about the end-to-end systems and the key component deep dives, and I will also briefly describe the remaining challenges. Now, before we start, let's do a very quick survey. Please raise your hand if you have used the Amazon Echo devices before. Wow, that really made me very happy. It's great to see the popularity of the Echo devices after its launch 4 years ago. So the Echo device is powered by Alexa, which allows the user to interact with a variety of applications to do a whole bunch of things. And we call these applications as Alexa skills. So what is Alexa? It is a virtual assistant like Google Assistant, Siri, Cortana, and etc. It is the brain behind Echo devices and all the 3P IoT devices that are integrated with Alexa. It can do 3 major types of things. First, complete tasks, answer questions, and also converse with users as a social bot. If we zoom into the task completion area, it can be further decomposed into the entity-based and the non-entity-based task completion. Here are some examples of entity-based task completion, which can be fulfilled by taking actions on entities through the service providers. And here are some examples of non-entity-based task completion for which there are no specific entities that the device is acting upon. So in today's talk, we will focus on the entity-based task completion. This is the very high-level overview of how Alexa works. In the middle, we have the speech platform, which can be thought of as the Alexa OS. And on the right, we have a list of critical services in the context of entity-based task completion, where ASR stands for the automatic speech recognition. NLU is our natural language understanding service, which maps the user utterance to an entity action pair. And then we route the traffic to the appropriate provider to take the actions. And finally, TTS is our text-to-speech service, which converts the text output to the Alexa voice. So in today's talk, we will focus on these parts. So in summary, this is the Alexa use model. She receives the user utterance in natural languages and route the traffic to the appropriate provider. There are two core technology pieces to make this happen. First, understand users' natural languages. And the second, to launch the service providers with the right entities and actions. We do so by creating a semantic representation of user tasks and the provider capabilities. And the maps them in this space of a semantic representation. So more specifically, here are some examples of the user atomic tasks. And we model each of them as an entity and action pair. For example, in this case, play is the action, raw is the entity, watch is the action, inception is the entity. Putting them together, we then form a knowledge graph of entity action pairs. And next, we represent each provider's capability via a list of entity action pairs that it supports in this knowledge graph. So with this, when the Alexa receives the user utterance in natural languages, it maps it to an entity action pair in our knowledge graph. And through this, route the traffic to the appropriate provider that can satisfy that task. So if we compare this diagram with the previous one, you can see that the main idea is to introduce this entity action knowledge graph and connect it to the natural language understanding and the provider ranking and routing. All right, so this is the high-level system diagram that integrates everything. Offline, we build the entity action knowledge graph. And at runtime, for example, given the user utterance Alexa, order food from Canlis, we apply the natural language interpretation on top of the speech recognition result to understand that this is about the local domain. User intent is to order food, which can be mapped to an action in our knowledge graph. And Canlis is the mention of the local entity in the user utterance that is often called as slot. Next, we run entity resolution, which takes the string mention, Canlis, from the user utterance and a search against the entity index to resolve it to an entity in our knowledge graph. And in this case, the resolved entity is the restaurant entity, Canlis Restaurant. By the way, this is a very, very good restaurant in Seattle. If you visit there, I highly recommend it. And in addition to resolving the entity, we also retrieve a set of action links from this action link table given the entity action pair, which will be used to deep launch the provider. And finally, in this provider ranking and routing module, we rank the action links and pick up the top one to deep launch the action service from the corresponding provider. So in summary, natural language interpretation is about domain and intent classification and slot detection. Entity resolution is about entity search, and the routing and the provider ranking and routing is about finding the appropriate provider to route the user traffic to. So now let's start with the offline stack, how we construct the entity action knowledge graph, as well as the corresponding entity index and the action link table. First, let's take a closer look at our knowledge graph. We model all the entities, including their properties, in our graph. Next, for each entity, we connect it to a list of all the supported actions. And finally, for each pair of entity and action, we have an action link to connect it to an action service in a provider. Please also note that one entity action pair may have multiple action links in the providers. For example, one can read a review from about a restaurant from Yelp, TripAdvisor, Zaga, and etc. So this slide shows how we semantically represent the entities and actions in our knowledge graph using the Alexa ontology. The ontology defines a set of entity types and action types. For each type, we also define a set of properties as the entity facts or action parameters. A type, so here are some examples of type, like this is the movie type, this is the people type, country, and we also have types corresponding to actions. A type also lives in a hierarchy, which means that it has some parent types, and it also inherits the properties from its parent. Another thing to note is that this Alexa ontology is fundamentally organized as a graph. For instance, an entity type can be linked to another entity type as its property. And similarly, all the action types and the entity types are linked to each other as well. Okay. So this is the system diagram about how to construct the entity action knowledge graph. We start from a list of multiple data sources, some of which are knowledge bases, such as Wikipedia, MusicBrain, and the others are provider catalogs that we get from providers, such as Amazon Music, Yelp, and etc. The key difference between these two is that usually the knowledge base just contains the facts of the entities, whereas the provider catalogs also define the supported actions and action links. They then go through the schema mapping to map the input data from the proprietary schema of the input sources to the Alexa ontology. We also built this ontology authoring tool, which is a self-service that can extend the Alexa ontology by adding the missing types and the properties that are found from the data sources. After that, the raw entities from these input sources are ingested into our entity action knowledge graph. And we also apply the entity linking and the entity merging on top of that, which will be described later. Finally, the data from the knowledge graph is published to entity index and the action link table to support the runtime entity resolution and the provider ranking and routing. Okay, so now let's talk about the entity linking. We call raw entities from the input data sources as source entities. And we also know that the data sources often have overlaps in the source entities. Like in this case, the same song entity Hello by Adele appears in Amazon Music, Spotify, Pandora, Wikipedia, and etc. So the goal of entity linking is to find the matched source entities across all those data sources. Why do we care about the entity linking? First, we need to deduplicate the source entities when we ingest them into our knowledge graph. Second, after the entity linking, we can aggregate the data from all the source entities belonging to the matched cluster. Later on, when we talk about entity resolution, you will see that the aggregated entity data will provide us with better entity matching and ranking signals for the entity search. As many data sources not only provide us with the information about the entities, but also the actions and action services about the entities. Aggregating the entity data across those data sources also give us a comprehensive list of all the supported actions and action providers for an entity. So those are the benefits of the entity linking. Now let's look at how we do entity linking. So this is the diagram of our linking engine with various computation modules involved. And we apply the machine learning model at the matching stage. What's at the bottom is our active learning-based self-serve pipeline to train the machine learning model that will be used in entity matching. This is an iterative process to sample the matched or unmatched pairs from the decision boundaries of our current production model, let judges label them, add them to our training set, retrain the model, and deploy that to our production system. So that entire workflow is kind of shown here. Another thing to note is that we use the incremental algorithm for the entity linking, which only updates the previous snapshot of the linking results with the changes from the latest data sources. So why do we use the incremental algorithm? First, obviously, it will save the computation cost, because the computation cost now is only proportional to the size of the data size change instead of the absolute size of the data sources. Second, the incremental algorithm will also increase the linking stability, because we will persist the linking result of unchanged source entities. Okay. Now let me walk you through this entity linking engine. First, we normalize the input data from multiple data sources to a standard format. But more importantly, we detect the new and change the source entities at this stage, which will be used to drive our incremental linking algorithm. Next, we do blocking. Because for entity linking, our goal is to find all pairs of matched source entities. So theoretically, we need to compute the pairwise similarity score for all possible pairs, which is very expensive, obviously. To reduce the computation cost, we first very quickly computed the hash keys of the entities based on the entity properties, and then create candidates of matched source entities with the same hash key. So we call this as blocking. Next, at the matching stage, we use the machine learning model to compute pairwise similarities of all the entities within the same blocks. And currently, we use the boosted decision tree model to compute the similarity score. We are also exploring using the deep learning techniques based on the entity embedding and SIMS neural network. So this is a simple example of entity matching. We first compute the property-wise matching scores. For example, in this case, the movie title matching score, movie release date matching score, and etc. And we feed those matching scores as features into our boosted decision tree to compute the final similarity score between a pair of two entities. Finally, we do clustering, whose goal is to group entities based on their similarity scores. And in particular, we use the bipartite matching for our incremental entity linking algorithm. As shown here, the left columns contains all the new and changed source entities, and the right column contains the clusters from previous linking results, which already group the matched source entities based on the previous data source input. And our goal here is for each of the source entities at the left column, find the matched cluster to join, or create a new cluster if we cannot find a good match. Another thing to note is that each cluster at the right column can form an entity by aggregating all the entity data from all the source entities belonging to that cluster. And we call that as a canonical entity. So in our bipartite matching algorithm, we do blocking and compute the pairwise similarity scores between the source entities and the canonical entities. And we make the final clustering decision. We say a source entity is eligible to join a cluster at the right column represented by a canonical entity if their pairwise matching similarity score is above a certain threshold. And finally, to get the final clustering result, we also apply some global optimization as regularization. For example, one source entity may be eligible to join multiple clusters purely based on the similarity scores, but we only pick up the top one. We don't allow multiple source entities from the same input data source to join the same cluster if we know that input data source usually don't have high duplicate rate. Okay, so that's how we get the clustering result, and that concludes our entity linking engine. And after entity linking, we do entity merging, which aggregates the entity data from all the source entities belonging to that linking cluster, and we form a canonical entity, as shown here. So there are a bunch of benefits of using the canonical entity in Alexa. First, it is independent of data sources, but has links to all the matched source entities. So it can be used to break the input data source silos. Second, with the canonical entity, we can aggregate all the entity data across data sources to, for example, for the entity search, for the entity resolution, we can get a better set of features for matching and ranking, as shown here. For example, we can get better surface forms, popularities, and other properties, and etc. We can also get a more comprehensive list of actions and action links for the provider ranking and routing. All right, so now let's move back to our overview of the system diagram. Let's look at our online pieces, the runtime pieces. We will skip the speech recognition and will only focus on the natural language interpretation, entity resolution, and provider ranking and routing. Let's first talk about the natural language interpretation. Let me check my time. Okay. Oh, sorry. Let's get back to the right slide. Yes. Okay. So let me first walk you through an utterance example. Alexa, play songs by the Rolling Brothers on Spotify. We first classify this utterance into a certain domain, and in this case, it is the music domain. One can think of a domain as a collection of similar intents and related entity types. We, in total, have 25 domains in Alexa, such as music, movie, book, product, smart home, local search, and etc. After domain classification, we then do intent classification. And in this case, the intent is play music. Intents are often actions, but there are also other types of intents, such as search, question answer, and etc. And finally, we do slot detection, which is just the domain-specific NER, named entity recognition, to recognize the noun phrases from the user utterance that correspond to entity dimensions. Like in this case, we recognize songs as the media type, Rolling Brothers as the artist name, Spotify as the service name. Besides detecting them as the entity dimensions, we also classify the entity types. So this diagram shows how we do the natural language interpretation at Alexa. It is based on two methods. The first one is finite state transducer, FST, which is based on grammar rules. Basically, it will take the input utterance and directly output the detected domain, intent, and a sequence of slots based on grammar matching. The second method is based on machine learning models, as shown here in this pipeline. Another thing to note is that in Alexa, we have a team for each domain. And I just said, previously, in total, right now, we have 25 domains. So in order for the domain teams to be decoupled, we replicate this pipeline for each of the 25 domains so that each domain team can independently train and deploy their domain classification and the corresponding domain-specific intent classification and the slot detection. And this architecture is crucial for Amazon to be able to move fast in each domain. What's shown at the bottom is our data-efficient self-serve domain-specific language feature development pipeline. One can think of a language feature as a particular user utterance patterns that we want to support at Alexa. For example, the pattern can be let Alexa user play the songs that he just listened to before. Usually, when we want to develop a new language feature, we start with grammar authoring and use FST to quickly support the natural language interpretation. In parallel, we also provide the self-serve pipeline to sample the training and the testing samples in a data-efficient way, and the machine learning tools to train the corresponding machine learning classifiers for the intent classification and the slot detection. Okay, so now this slide gives you a quick comparison of FST versus the machine learning model. FST is grammar-driven, while the machine learning model is data-driven. It is easier to bootstrap a new feature with code start via FST, while machine learning model needs a data collection and annotation stage to get the training and the testing samples. FST usually has high precision but low recall. Machine learning model can be used to improve recall. In our production, we use a combination of FST and the machine learning model so that we can quickly launch new language features and support continuous recall improvement. This example shows how we use FST in natural language interpretation at Alexa. It is essentially a finite state machine, which takes a sequence of strings from the user utterance as the input and outputs another sequence of strings representing the detected intent and slots. Like in this example, the dots are all the states, and it takes the input strings and output in this case, the intent, and also in this case, the slot. Okay, it is a very standard way. People also use it in speech recognition, as well as the natural language interpretation. Now let's talk about our machine learning method in the natural language interpretation. Let's start with domain classification. We used a binary classifier for each of the 25 domains so that we can decouple those domains, because all those binary classifiers can be trained and run independently. More specifically, our classifier uses an ensemble of logistic regression and the deep learning models. To support the data-efficient learning, we use the active learning and the transfer learning. The slot detection is just the domain-specific NER and the sequence tagging. CIF is widely used in sequence tagging, but instead of using a predefined set of binary features for CIF, we use the convolutional neural network to automatically learn a set of continuous valued features for CIF. And more specifically, like this diagram showing our deep learning based model for slot detection, the bottom layer is the standard word embedding, and we add the convolutional network layer for the automatic feature extraction, and the output layer is CIF. And similar to domain classification, we use active learning and transfer learning for data efficient learning. And finally, slot classification is basically a domain-specific multi-class classifier for each domain. And very similar to domain classification, it uses an ensemble of multinomial logistic regression an ensemble of multinomial logistic regression and the deep learning models. We also support the data efficient learning, which is very, very important for Alexa production. Okay. So now let's talk about the entity resolution. It takes the output of the natural language interpretation result, form the entity search query against the entity index, and retrieve a set of relevant entities to act upon. There are three problems of entity resolution. The first one is name search, where the entity is mentioned via its name or alias. Like in this example, album 21 is the mention of the entity. And our goal is to resolve the mention to the entity in our knowledge graph. The second one is graph search, where the entity is referenced as properties of other entities, like Adele's second album. So the entity is not explicitly mentioned. And we traverse the knowledge graph to retrieve the target entity. The third one is category search, where the entity needs to match with a list of constraints. Like in this example, it needs to match with restaurants as the local business category, Thai as the cuisine type, and kid-friendly as the local business attribute. So we have three different types of entity resolution problems. This is our entity resolution system, again at a very high level. When it receives the entity query, it first performs the query understanding and alteration. Then we run federated search against multiple data sources, and I will explain why we do that later. When we receive the entity results from multiple data sources, obviously we need to do deduping and form a set of candidate entities. And then we do another post-federated search ranking, followed by the result truncation based on the query type from the query understanding module. Okay, so what do we do for query understanding and alteration? For query understanding, we need to differentiate single intent versus list intent, which will be used to determine how aggressively we want to truncate the search results. The query alteration contains two subtasks. Transliteration is used to normalize the text output from the speech recognition to the canonical written script. For example, Japanese has 3 written scripts, and we normalize to one of them. And it's similar to Hindi language. In query expansion, we add synonyms to our search query terms, which will help us increase the match recall. Now, this slide explains why we do the federated search. Because we have multiple 1P domain teams, and we also integrate Alexa with the 3P developers. Some developers need to have larger search control over their catalog entities. That's why we allow them to build dedicated domain and provider indexes. And that index will be based on their source entities. The universal index is built from our own knowledge graph using the canonical entities in our knowledge graph. And finally, we also send search to the knowledge graph to support the graph search. For entity deduping, we leverage the entity linking result by mapping the returned source entities to the canonical entities, and we can dedupe using them. We use machine learning-based ranking models in 3 places. Each of the domain and the provider indices has its dedicated machine learning-based model as the ranker. The universal index has a machine learning ranker as well as the post-federated search ranking. So right now, for all those ranking models, they are based on the, where is my pointer? They're based on gradient boosted trees. And we have 2 major types of ranking features. First, query match against the entity names, descriptions, attributes, and etc. And second, the entity popularities. Also note that because the universal index and the post-federated search ranking use the canonical entities, which aggregate the entity data across data sources, so they will have better matching and ranking features. All right, so finally we do result truncation, which has two goals. First, we want to suppress irrelevant results from federated search. Some of the domain teams or 3P providers, they just very aggressively return the entity results, and sometimes they even do spam. So we need to suppress them. Second, we want to aggressively suppress results for the single intent. Of course, ideally, we should only return one entity if the intent is single, but sometimes we still allow multiple results due to ambiguities. All right. Another thing to note is that sometimes one utterance can be classified into multiple domains and intents due to ambiguities. Like in this example, the utterance is play Michael Jackson. It actually triggered multiple domains and intents. We treat each of them as a hypothesis, and we use a hypothesis re-ranker to rank and pick up the most likely one. This is what we mean as late decision binding. And specifically, we use a deep learning-based model for the hypothesis re-ranking. So for each hypothesis, we have a vector to encode domain, intent, a sequence of slots, resolved entity, and the scores. And we also append that vector with the contextual signals, such as domain popularities, the usage history, whether that user, constantly use that domain quite often before or not, as well as the device type. For example, if this is Echo Show, obviously, user can play video, but if it's just a regular Echo speaker, we should bias towards, for example, for the same thing, it can be video or music, we should bias towards music. Okay. So, and finally, in this network, the output layer is the softmax across all the hypotheses, which will let us select the most probable one. Okay. So now let's talk about provider ranking and routing. We know that from all the previous steps, we mapped the user utterance to an entity action pair in our knowledge graph. For provider ranking and routing, it first retrieves a list of action links from the action link table, and then ranks and then select the best action link to deep launch the corresponding provider. Our action link table is simply a key value lookup table with the entity action pair as the key and provider action link as the value. So it's very simple. You just pass it the entity action pair, and you'll get providers and action links. So this is the list of all the ranking signals that we use in the provider ranking. So in our production, finally, we use a combination of selection rules. For example, we look at whether that user has some personal preference and we boost it, or whether it has some, whether he or she has some subscription to some specific service, and we also boost that service, as well as a very simple linear-based ranker based on those signals. And finally, we pick up the top-ranked provider and the corresponding action link, and we use that to route the traffic to that provider. Okay. So with that, I will conclude my talk with all the remaining challenges. Let's start at high level. First, we want to continue scale our experiences to more 1P domains, 3P applications, locales and endpoints. And second, once we grow the domains that we support at Alexa, we will see more NLU, natural language understanding, ambiguities, answer relevance challenges across those domains. And finally, besides growing fast, we also want to improve our end-to-end measurement of the product quality. At a component level, obviously we want to continuously improve our speech recognition and spoken language understanding. We definitely want to promote more usage of Alexa in the conversation mode by better dialogue management. We want to improve our natural language generation so that the Alexa voice will be more natural. And finally, to make Alexa as a truly useful personal assistant, we want it to be more proactive and personalized. And finally, as you may know that in Amazon, we call every day as day one to keep ourselves as a growth mindset. This is certainly true for Alexa. So that's it for my talk. Thank you. Yeah, so we should still have plenty of time for me to answer questions.
Thank you, Xiaodong. Questions from the audience?
A simple question. I really enjoyed the talk. Can you make us
Thank you.
available afterwards?
I will check with my company. Yeah. So because I also just recently joined Amazon, I know every company has a policy for that. Yeah.
So we will have the talk itself available. So as far as yeah, so we have a video and there will be slides in the background. We won't be actually sharing slides for this talk, but the talk itself will be available. Okay.
Thanks, Darren. Other questions? Yes.
Just a question about the technology that you use for the naming recognition. What kind of framework or technology do you use, like maybe BERT or TensorFlow or Spacey that is going through in the market? Do you know what decision took Amazon in the technology framework?
The knowledge framework?
No, in the naming.
Yeah, NER. Yeah. So NER, as I showed earlier, so basically we just use this CNN plus the CIF for the sequence tagging. So that's the techniques that we use for NER. And this is domain specific in a sense that for each domain we have a specific model.
But there is any framework or technology that you use for the CNN to create a CNN? Or
No, we just use regular, CNN. Yeah, no, not any particular framework. By framework, you mean?
like a TensorFlow?
Oh, TensorFlow. Okay, I see. So yes, in Alexa, it actually doesn't matter whether we use, TensorFlow or PyTorch or whatever. So but in our choice, we do use TensorFlow. Yeah.
So when you talk about the machine learning-based natural language interpretation, you mentioned about active learning in like CNN and CRF. So could you give me more details about how do you do active learning, like in a heuristic way or by reinforcement learning?
Okay, so it's kind of a heuristic. It's not based on the reinforcement learning. So essentially, what we do is we first have a sort of a crude model based on smaller set of samples, and then we sample from the decision boundaries, and we label them, and it is an iterative process of sampling, label, retrain, sampling, label, retrain until we hit the target.
Sometimes Alexa becomes randomly active. For example, we are talking to somebody else, or even if the television mentions the name Alexa somehow. So it's quite surprising to me because looking at the architecture, it seems that it should be able to contextualize, the phrase and or not. So my question is, where does it fail?
Okay, so so basically Alexa has two phases. Okay, the architecture that I show is the phase that we already detect that you are talking to Alexa, and we use the contextual information. But before that, we have this wake word detection. It is sort of based on whether the device hears Alexa or not, and we don't want to, before we detect the wake word. Do all the recognition, particularly send the signals to the cloud because that violates the user privacy. At this moment, it is not a multimodal detection of the this Alexa wake mode. It is just based on whether it hears the Alexa or not. So not a whole bunch of other signals can be used, but the team is also looking at in the context of first, not violating the user privacy. Second, how we reduce the false positive of the wake word detection, leveraging some other signals to better improve its accuracy. So this is an active research area.
I have a little question that's probably half silly, half serious.
No silly questions.
Yeah. As you walk around Melbourne, you will hear the Australian accent, which, I spent most of my life in Australia, but speaking from people from other parts of the world, the Australian accent is not necessarily easy to understand a lot of times. And in terms of relative to the English-speaking population, Australia being only 25 million people, it's also a relatively low percentage of the English-speaking population. So my question is that for something like Alexa to deal with this both quite heavy and relatively less frequent accent, what are some of the challenges you experience on that front, and how do you deal with it?
So first of all, I'm not a speech recognition person, but I know in Alexa, what it does is basically just deploy different model for each locale. So we does treat the Australian as its own locale, different from, for example, US or Britain. So we have a dedicated model that customized to the Australian accent.
I have perhaps a slightly open-ended question. One of the things that I worry about in the space has been the fact that actually closing the loop to get the user feedback to actually improve the system is really quite difficult, because a lot of times, for example, you give an answer and there's really no user response as to whether it was good or bad or annoying or whatever. Can you talk a little bit more about how you're thinking about how to close the loop to actually get the assistant to truly learn on?
Yeah. First of all, actually, your observations are spot on. The user feedback is actively studied and used in Alexa. It is at this moment it is quite domain specific. For example, if in the music domain, we do actually look at the play duration of the music, and usually we say if it is shorter than 30 seconds, we think this is negative user feedback. And in some other cases, we also look at the signals like users is starting to barge in with Alexa, and we also use that. And we also do the emotion detection from the user response. But of course, we really envision that in the future, with more and more devices, with this camera capability, and we can really use the multimodal signals. We can also look at the user, some kind of user body or whatever behavior to detect whether it is the positive feedback or negative feedback. But I totally agree with you. Feedback is very useful. In Alexa, it is far harder than text-based.
So you mentioned so there are multiple different devices like querying different domains. So within the different domains, are you using the same exact same models but with different parameter set, or using a completely different approach?
Similar model architecture, and because that also let us use the transfer learning capability, and this is a very important method for us to do data efficient learning.
So do you guys do any kind of A/B experimentation with Alexa, and or any kind of changes that you introduce to your
Yes, we do.
Alexa quite a bit at home for music, and
Great.
it's actually narrowed my world down a little bit, because when I use a UI, there's usually recommendations, and I get more diversity, and I can try other things. So when I have to produce it, it's kind of like having a blank piece of paper. I end up saying the same thing all the time, and I always end up listening to the same music. What's going on from a diversity standpoint?
Yeah, so the music domain team is actually working on that, and to improve the diversity, and specifically to enable better music recommendation. It is an ongoing project. Does that answer your question? Yes.
I'll follow up to that question. I think one of the issues in this space, as I understand it, is the great majority of the use case indeed is music. So one, the reason is really because it's actually quite difficult for users to discover what actions are even available on the device. Can you speak a little bit more about what you guys are doing in this space of getting user educated and actually getting them to discover the actions that are possible?
Yes, so it's actually a combination of actions and domains. So we do see that many other domains are not very highly utilized. I think it is a combination of two things. One is I have to be honest that our quality in those domains are not as good as music, and also compared to, for example, some of the commercial search engines that are already there. We still see some gap. So this is something that we're actively working on. And in terms of the discovery, we actually do see that particularly, let's say new users, when they open up the box, they actually do want to see and try all different domains. So we actually want to leverage that opportunity while we improve the quality in those domains to basically show user the greater capabilities that Alexa can do. And there are some other methodologies. For example, we have the Alexa app. We can push those news about new skills. And in terms of the 3P skills, at this moment, they don't get enough traffic from Alexa. Part of the reason is that, unlike what I've shown here, many skills, they are not integrated with this system, which means that users still have to invoke the skills using the skill name, and that significantly reduces the capability for user to discover those skills and also interact with the skills. So we do want more skills to be integrated into the systems that I just introduced, because with that, it's basically by intent, right? So that thing with the combination of, quote unquote, educating user with more domain capabilities, intent capabilities, we also want Alexa users to sort of, discover those skills, but not by naming the skill names.
So I have a question more about the bigger picture of the strategy as day one you mentioned in the last slide.
Yes.
That's because I know that there was a lot of shareholder letters talking about day one strategy that they focus on fast movements and fast growing of the company. And my question is towards the research point of view, how do you distinguish in the way of to implement your day one strategy in the research field? So I'm asking this for more about the future research people who may be concerned about joining Amazon in the future, and how does your research environment distinguish from other research environments?
Wow. Okay. So we do embrace the researchers to work closely with us. Inside Alexa, we actually integrate applied researchers, we call them as applied scientists, to work very closely with the production team. We actually put them in the same production area and work very closely to bring their innovations directly to the product. And we also work closely with academia. So there is this, Alexa challenge. I don't know whether you have heard that or not. So basically, this is to create these opportunities for the academia to work with us to improve the conversation of the Alexa, or in general, this conversation AI.
So currently, Alexa takes the connection between questions into consideration. So for example, I get a question, play A, and after a few minutes I say play B. Then I think B is not what I really like, so I go back to the previous question.
Yeah, this is actually the one of the feedback signals that we are using. This is kind of a more like a session-based feedback.
Okay.
Yeah.
So if we take this on one step further, that will be will Alexa actually consider the task in one session to go a higher level to say what will be the target for the user doing in this session?
Yes. So this is the multi-turn dialoguing, which is not covered in my talk, but in Alexa, this is definitely very important, particularly with this voice user interface. We see users, just naturally do more and more of this kind of a conversation, and we definitely want to encourage that. Yes.
So, thank you, Xiaodong.
Thanks.